Welcome back, everybody. In this lesson, we're going to be talking about the quadrilateral's angle sum and what that angle sum will be like for any quadrilateral, similar to what we did with triangle angle sums a few lessons ago. So by the time we're done here, we should be able to answer two main questions or types of questions. The first is, what is the interior angle sum of any quadrilateral? So we know for triangles it was 180 degrees. Of course, it should be different for a different polygon, so we should be able to answer that. And the second is, how do I find missing angle measures of a quadrilateral based on the information we're going to get from the first question? So let's go ahead and jump into this. So we'll start with that first question. What is the interior angle sum of any quadrilateral? And to do that, we're going to need a quadrilateral to look at. So here we have quadrilateral ABCD. And we want to know something about all of these angles and what they're all going to add up to and how that could impact any quadrilateral. And what we're actually going to do is we're just going to use what we already know about interior angle sums. And what we already know is, well, actually about a triangle. So you might wonder, well, how do I use a triangle to help me with a quadrilateral? So what we're going to do is we're actually going to split this polygon into as many smaller triangles as we can. But when we do it, we can't have any of our lines overlap. Here's what I mean. I'm going to go ahead and connect vertex A down here to vertex C. It's not a very good line. And by doing that, I'm in essence trying to cut this quadrilateral into smaller triangles. So I have triangle 1 up here and triangle 2 here. And I've got two triangles. Now, could I do this again and get more triangles? I could cut the polygon again. I mean, I could cut from D to B, and you're like, oh, look, I've got all these smaller triangles. But again, now I've got this green line overlapping or cutting through the red line, and that's a no-no. So we're not going to do that. So it looks like I can't connect any more of the corners or any more of the vertices to get smaller triangles. So what have we learned? Basically, we've learned that I can take any quadrilateral and connect it corner to corner and divide it into one, two smaller triangles. What do we know about that? Well, we know that a triangle, like triangle ADC up here, that has an interior angle sum of 180 degrees. We already have that information from our previous lessons. But that means that ABC down here, well, that also has an interior angle sum of 180 degrees. And since these two triangles, when you stick them back together, you get the quadrilateral. That means that we should be able to take both interior angle sums of the triangles, 180 and 180, and find their sum to get the total interior angle sum of our quadrilateral. And of course, 180 plus 180 is 0 plus 0 is 0, 8 plus 8 is 16, and 1 plus 1 plus 1 is 3. And voila, the interior angle sum of any quadrilateral, guys, is always going to be 360 degrees. We're going to look at one more quadrilateral, though, to really help kind of prove that this wasn't just a fluke with this one specific quadrilateral we had here. So we're briefly going to look at this rectangle now, and again, in a different way, also prove that the interior angle sum should still be 360 degrees. Now, we could do the same idea as last time. I mean, we could connect one vertex to the other. You get two triangles, and you add up the 180 plus 180 degrees for each triangle, and you'd still get 360, and that's great, but that doesn't help us prove anything differently. So I used a rectangle, and a square could have worked as well, because we already actually know the interior angle measures of those figures. Based on the definitions and the properties that we wrote down in the last video, we actually know that each one of the angles is a right angle, meaning that each one of them is 90 degrees. So since in this quadrilateral we already have those measures to find that angle sum, we know we can just add up all of those measurements, or 90 degrees 4 times. And it just so happens, we do all the zeros, which is still 0, and 9 4 times, that's 36, and one more time we can see, hey, we really will get 360 degrees. So whether we use the triangle approach or whether we prove it with something like a rectangle or a square, we can see that the interior angle sum of any quadrilateral is always going to be 360 degrees. So we could do a couple things with that information. Like with triangles, we could take a look at four angles and say, do they have a sum of 360? Will it really be a quadrilateral? That's kind of a basic level thing for us. But then we can also use it to find missing information, which is what we'll look at next. So here we have a quadrilateral, more specifically a trapezoid, where we're going to have to find some missing information, specifically the missing angle measure labeled x right down here. But based on the angle sum theorems that we're already familiar with, we know that if we add the measures of all of the interior angles with a quadrilateral, we should get a sum of 360 degrees. So that's what we're going to do here. We're going to go ahead and take 80 degrees plus 75 degrees, and I'm going to keep all the constants together, so plus 105 degrees next, plus x, and that should automatically equal our 360 degrees. So similar to our work with triangles, of course, what we need to do is go ahead and simplify any like terms that we can in this first expression. So 80 plus 75 plus 105. I'm going to go ahead and I think add, since addition allows us to use either the associative or commutative properties here, I'll go ahead and add these two first because I want to make an even 10. I see that 75 and 105, that would make 180. We still have the 80 up front, so 80 plus 180 plus x, and again, we know that that should equal 360. We still have some like terms, so we'll go ahead and simplify again. And 80 plus 180 appears that it would be 260 degrees plus x. Now, when you guys are working on your own, I would encourage you guys to use some strategies like this, especially if you don't have a calculator handy, meaning adding two numbers at a time. But if you have a calculator handy, you guys might be able to go ahead and simplify all of this at one time. As long as you're showing your steps, that should work out fine as well. All right, at this point, it's time to go ahead and solve for x. To go ahead and isolate the variable over here, we just need to go ahead and get rid of this constant, and to cancel out a 260, we're going to subtract 260. But the rules of algebra, those properties of equality, says to do that to both sides, and we'll simplify. Of course, 260 minus 260 is 0, so those cancel out. We are left with an x, though. And 360 minus 260 is 100. So it looks like we finally found x. Now, in this case, again, it does happen to appear that x will describe the actual angle measure. So I want you guys just to take a moment when you're working on these problems, when you get an answer for x or the angle size, whichever one's appropriate, I want you guys to look at them and say, does that answer actually make sense? Here's what I mean. We have angles like these two at the top, the 80 and the 75. And visually speaking, they both appear to be acute angles. And that's good news because, I mean, they're both acute measurements. 80 is less than 90 degrees. 75 is less than 90 degrees, so that makes sense. So when we're looking at these other angles down here, and of course angle x, what type of angles visually do they appear to be? Are they acute or are they obtuse? Do they look like right angles and so on? Now the one here on the left, that does appear to be an obtuse angle. Obtuse means we should have a measure greater than 90, and 105 is greater than 90, so that's great. But using that idea, I want you to apply it to x. What type of angle does angle x visually appear to be? To me, it looks like x is an obtuse angle. So I was already before I even started imagining to myself that I know I want x to come out to be a number greater than 90. If that doesn't happen, I'd be a little bit concerned and I'd want to take time to maybe rework the problem or see if something else had happened. But here, of course, we can see, well, x really did come out to be greater than 90. 100 degrees is definitely greater than 90 degrees. So that's just one way for me to use some common sense to say, does my answer really make sense in terms of whatever my situation is? So that's how we'll use that angle sum idea for quadrilaterals as well. So going back to the start, were we able to answer these two questions by the time we were done here with our lesson? First, what is the interior angle sum of any quadrilateral? Take a second, answer to yourself. If you said 360 degrees. You're doing a great job. Every quadrilateral has that interior angle sum of 360 degrees. Next, how do I find the missing angle measures of a quadrilateral? Were we able to work through that and discover how that worked? And I think we certainly were. In our last example, we were able to see that if you write an equation that adds up all of the angle measures and sets it equal to the total sum, which is 360 degrees, we should be able to use some algebra to solve for our missing information. So I think we were able to work through everything okay, and hopefully these ideas will help you take a look at quadrilaterals and their angle sums on your next assignment. As always, let me know if you have any questions or meet with me virtually for tutorials, and good luck to everybody. I will see you guys next time.